We're going to start off this lecture by looking at internal resistance. This is internal resistance of a battery. A real-life battery is not perfect. Internal resistance to the flow of electricity will occur. Similar to how there's no such thing as a frictionless surface, there really is no such thing as a battery without internal resistance. So here's a picture of a battery. This is a car battery, and you'll see there's this resistor out here. Maybe it's a headlamp or a light or the heater of the car. And inside the battery, we have this internal resistance to the flow of electricity. And the way you handle that is you just treat that internal resistor as just a resistor in the circuit. It's in series with this battery. And you'll notice here that this is the positive terminal of the battery right here at this point. This is the negative terminal of the battery right here at this point. And there's something that we're going to look at called terminal voltage. Now let's say this is a 12-volt battery. We would have to subtract away the voltage drop across this internal resistor to find out what the terminal voltage out here is. So if this is a 12-volt battery, and let's say there's 2 volts dropped across this resistor, the terminal voltage here would have been 10 volts. So the terminal voltage is the potential difference across the terminals of the battery, which include the internal resistance of the battery. In other words, you subtract away the voltage drop across that internal resistance. We're now going to look at what's called Kirchhoff's rules. These are rules for circuits. The first rule is the junction rule. The junction rule is the sum of the magnitudes of the currents directed into a junction equals the sum of the magnitudes of the currents directed out of the junction. It's pretty self-explanatory in the drawing. If you have 7 amps of current coming into a junction, you can have 5 amps and 2 amps come out for a total of 7. So if you have 7 amps coming in, 7 amps will come out. The next rule is called the loop rule. Around any closed circuit, the sum of the potential drops equals the sum of the potential rises. We've been using this rule already. We said that the voltage gained by the power supply is equal to the voltage drops within the circuit. This is let's just call it the loop rule. So if you look at an example here, we have figure 20.29 shows a circuit that contains 2 batteries and 2 resistors. Determine the current I in the circuit. So we want to know what this current is. Now, we'll go around and treat each of these resistors as if there's a voltage drop here. And what you do here is this 24-volt battery is the larger battery. So, and the 6-volt battery is the smaller battery, and they oppose each other. This 6-volt battery is trying to have current go to the left. This 24-volt battery is trying to have current go to the left, so they're going to actually oppose each other. So this is actually going to be a minus 6 volts right here. So you're going to have positive 24 volts, minus the voltage drop here. Voltage is calculated by I times R, so it's I times 12, minus the 6 volts, minus the I times 8 voltage drop across this resistor here. And so what we've done is we've gone in a loop and we set all the voltage drops equal to voltage gains. So here's a voltage drop, here's a voltage drop, here's a voltage drop. So we're going to say this 24 volts equals I times R minus 6 I times R. The next section we're going to look at is how does an ammeter and a voltmeter work? So the measurement of current and voltage. And since an ammeter is an instrument that measures current, it must be inserted into the circuit so that the current passes directly through it. In other words, an ammeter is placed in series in the circuit. So here's a picture of that. We have this battery down here, and the electricity comes out of the positive side, goes through the resistor, comes through the ammeter, comes out, and we have the circuit. The ammeter is in series with the circuit. The way this resistor is set up is that the shunt resistor lets most of the current pass through just a small amount, or shunt resistor lets a large amount of the current pass through, and then the small amount goes through the galvanometer. Galvanometers are set up to have very small currents pass through. So what we have is the current comes into the ammeter, 59.9 milliamps go this way, and let's say it's 60 milliamps total goes into the ammeter. 59.9 milliamps goes this way, leaving 0.1 milliamps to go through the galvanometer. So an ammeter is set up in parallel. It has the shunt resistor, and in parallel to that is the resistance of the galvanometer. The voltmeter, on the other hand, is an instrument that measures the voltage between 2 points, A and B, in a circuit. Figure 20.34 shows that the voltmeter must be connected between the points and is not inserted into the circuit as the ammeter is. The voltmeter is placed in the circuit in parallel, not in series. So here's our picture of the voltmeter. You'll notice that we have our circuit here, and the voltmeter is set up on either side of the resistor. We're looking at what the voltage drop between points A and B would be. And very little current goes into the voltmeter since the voltmeter has a very high resistance. And again, the galvanometer measures the amount of current. So what happens is the current's flowing along here. Most of the current goes right through this resistor, and some of it leaks into the voltmeter, into the galvanometer. So what you have to do is you have to make this resistor here fairly high, so not as much current goes through it. You only want 0.1 milliamps to go through it. Let's say 60 milliamps are coming along. You want 59.9 milliamps to go this way, and 0.1 milliamps to go through the galvanometer. So this, actually, you put a voltmeter in parallel to the circuit, but the voltmeter itself is wired in series.